calm but violent like Ben Siegel. I'm anti-evil, plus I touch a desert eagle. My life's illegal, slaves and prisons are equal. The devil's lethal, he killed 100 million people. I'm Dark Man, Iceman, Lao, Wu-Tang Clan, Traficanti, Sensei, Comprende. My Marine Corps, straight from the Trojan War. Black Cape Crusader, trapdoor, flamethrower, stuck a chain store when I was dirt poor for my reward. Next week the Germans had me on the bulletin board. I beat that case, they couldn't identify my face. I'm triple darkness, silencer I have you erased. Me and my Wu pirates start riots with Osiris. Math, I apply it, kill you, but I'm quiet. Respect the abbot, it's love or lost. Shine like a shooting star, sting with the cobra claw. What? New world order, 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 new world order.
Yo, I enter through the cave of your ear in a high-pitched, silent tone only a dog could hear and impregnate you with the wisdom of the woo. Then your subconscious dreams come consciously true. Have you in such deep thought? Your pulse and blood pressure so low, you diagnosis corpse. Having out-of-body experience, clear no interference. Everything with physical form, lose appearance, become one with the formless. Now you feel your strongest. Escape time, realize you live for the longest. Love 1,000 years in a day. Without opening your mouth, you say everything you wanted to say. Attracted to the core of the earth, I stay grounded. The sun in the center of this, I'm surrounded by planets in the mist that spins the wind chill. But my light melts a snowflake for 93 mil. All who have an ear, let them hear as we build. Cause one ear of corn can produce a cornfield, and one cornfield can produce the cornmeal. The bread from the body of Christ, all is filled with the truth of life inside your bone marrow. You can make it physical as large as your shadow. Whether space is cyber or optic is fiber. Become a Wu multimedia subscriber and hibernate the root tape in your mental state. Let it meditate. Sit back and await the orders. For this you don't need no tape recorder. So let's prepare for the Wu world order. 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 We coming soon and we striking at your borders.
All right, so today we're going to focus on asymptotics, which is the fifth step in our algorithm analysis process, excuse me, where, again, the first three are a setup. We identify the input size, and then we choose which elementary operation that we want to analyze the algorithm with respect to. After we've gone through the analysis, the actual analysis of coming up with a function, a resource function, that computes, what the resource is based on what the input size is. Then what we need to do is we need to analyze that and give that a big O asymptotic characterization. Again, it's step 5. All you're doing is simplifying that function that you derived in step 4. The motivation here is that you simply just want a classification, a characterization of the algorithm's performance or efficiency. Any algorithm that performs n squared quadratic is going to perform the same way, because if you take a calc attitude or if you take an algebraic attitude towards it, it's going to have the same rate of growth. If a linear function and a linear function, there's really no difference between those two things. We're only interested in how an algorithm performs as the input size n grows towards infinity. We're only interested in the growth rate. We're not interested in these constants that are sitting out front here. Oh, just a second. One second. The audio is fine, but let's go ahead and get rid of that second mic there. There we go. That should work. All right. Hopefully that works. And we're good. All right. All right. So we want to analyze it with respect to the growth rate as n tends towards infinity. We're not interested in algorithms that perform well on small inputs because that can be deceptive. But two, we're not always going to be running this on small input sizes. We're going to be running this on larger and larger data inputs. So we want those two things. We want our analysis to only focus on the rate of growth. We want to ignore constants and lower order terms. Right? And the tool that we're going to be using is big O asymptotics analysis. All right? And this tool actually goes back to the invention of calculus. Its original definition is in terms of limits, but don't worry about that. We're not going to require calculus here. Instead, we're going to give you the following definition, which is in terms of algebra. Right? So let f of n and g of n be two functions. We want to compare these two functions. We want to compare their growth rates. For our purposes, they represent the complexity of two algorithms a and b. Right? We say that f of n is big O of g of n if there is a positive constant c and an integer n naught such that at some point f of n is less than or equal to c sub g of n for all n greater than or equal to n naught. Right? Now, don't worry about that definition. Think about the visualization of this. In fact, I've got a better visualization over here. Right? So what I've got here is 175 n squared plus 50n plus 1. Right? If I only, and then I've got n cubed. Which one of those is intuitively bigger? Right? Which one has the larger order of growth? The one where it's quadratic or the one where it's cubic? Right? Hopefully you answer the one where it's cubic. That should be larger. But according to the graph here, it's lower, right? That means it's taking less resources, fewer time, less memory than the one taking n squared. But that's only because we're focusing on small input sizes here. Input sizes up to 100 here. If I zoom out a little bit, what I see, if I go from 0 to 200 here, is that at some point there's a crossover point where after that, this function will always dominate. In fact, if I zoom out here to 1,000, right, then it will become absolutely apparent that this function is a higher order of a higher rate of growth. Right? At that point, whatever that crossover point was, this function will take more resources, more time, more memory than this algorithm over here. Therefore, this algorithm, even though it performs poorly on small input sizes, is the better one overall. Right? That's what this definition is saying. The n naught here is that crossover point, that 175 or whatever. We're going to solve for that eventually. That at some point, right, then this function after that point is always going to dominate that function on the bottom. Right? And we say that f of n is big O of n. Right? And we write that f of n is equal to big O of g of n, right, if that's the case. There we go. All good now? Yep, we're good. All right. So technically, oops, sorry, that should be math right there. Technically, it should be like this. Right? If you've never seen that before, you probably see it in 235. Don't worry about that, though. We're just going to go ahead and abuse the notation and say that it's equal to this thing. It's actually like this. Why? Because this big O over here is a set of functions. It is a class of functions, all functions that have the same order of growth or greater order of growth than f of n. So it's more correct to use this, this set notation here, but it's so common that we just do this. Okay, so don't worry about it. Again, big O characterizes the relative rate of growth of two functions, right? As n tends towards infinity, right arrow, infinity. There we go, math, right? F of n has a less than or equal to order of growth, rate of growth, I should say, rate of growth as g of n.
when we write that, right? Another way of putting this is that g of n's growth rate is at least as big as, let me emphasize that, at least as big as that of f of n. Right? They could be equal. They could have the same rate of growth. It is only a relative measure. Right? So, for example, here's some basic examples. Right? If I were to write the following, for example, say 3n. All right, let's go to math mode here. 3n plus 3. Right? It is correct to say that this is order of n. Right? Why? Because this is a linear function, and order n is characterizing all linear functions. That is true. Right? But it's also true to say that 3 of n plus 3 is big O of n squared. Right? That's also true. Why? Because n squared is a larger order of growth rate. Remember that this is a less than or equal to right here. Right? So the thing on the right-hand side is as big as the thing on the left-hand side. Right? And this is another reason that we kind of use and abuse that notation of equals there. 3 of n, of course, it's also true that 3 of n plus 3 is order n cubed. Right? You can keep going, right? It's also order n, or 2 to the n, right? Which is going to be exponential there. These things are all true, right? Now, this one is the most true, or the most technically true. It's the tightest bound, right? So this is the tightest bound, tightest possible bound, right? That's the point where it's actually equal in this expression up here. Basically, that's what we're doing. But these are loose bounds, tightest bound, right? This is a loose bound, looser bounds. Right? What is not true, though, is that 3 of n plus 3 is not going to be, say, order, say, logarithmic. Let me fix that. There we go. All math mode here. There we go. It is not that, or sorry, that is not true at all. Right? Why? Because the thing on the right-hand side, logarithmic, that has a lower order of growth, a lower rate of growth than a linear function. So that's definitely not true. In fact, if you reverse most of these loose bounds right here, none of those things are true. So for example, it's not true that, say, n squared is big O of n, right? That is definitely not true, okay? So what are we doing here, right? Again, big O analysis provides an upper bound on the rate of growth of a function, right? It is not necessarily a tight bound, right? It can be, but doesn't have to be, right? All right, so great. How do we go about doing these things? That means that we need to have some sort of proofs, right? So given two functions, f of n and g of n, we have to come up with a proof that says that f of n is order of g of n. Now, the first thing that you do, first step, is to write out your intuition. So, for example, if I had, say, two functions, say f of n is 175 n squared plus what was that value that we had? 50n plus 1 plus 50n plus 1. And say g sub n is n cubed. Right? Then clearly my intuition tells me that this is the higher order of growth. Why? Because I know polynomials, and larger polynomials grow faster than lower order polynomials. Now, you might ask yourself, well, what if it's not like that? What if it's like this? Right? Yeah, you could go ahead and swap those. So I'm going to go ahead and swap those immediately and always put the larger one as g of n. Because what I want to do is I want to show that f of n is going to be order g of n. Right? So if they're out of order, go ahead and just swap them. Right? You can show the opposite direction. Right? That's called a lower bound. And that's going to be that's going to be omega. Right? Not big O, but omega. And we're not going to get into that at all. All right? So you write down that my intuition says it seems that f of n is big O of g of n for these two functions right here. But now I need to go about setting down an actual proof. Okay? There are two approaches here that you can take. Approach A is to find the crossover point. Remember this over here? Let me go ahead and zoom into only 200 here. I need to find that crossover point right there that fits the definition. And I'm going to say that after that point, this one is always going to be greater. Right? Why? Because that's the definition. You find an n naught, and then basically you're fixing c to be 1 here, and then you're finding that n naught. So that's the first algebraic technique. We're going to find the crossover point, the largest value n for which the two functions intersect. After that point, you know that they never intersect again. And so you can come up with an inequality easy that way. Right? There's another technique where you set up an inequality. It's a much easier technique that we'll look at here in a second. You set up an inequality and make your function bigger and bigger and bigger until it matches g of n. Okay? Otherwise, technique C is going to require some calculus. Don't worry about it. All right, we will cover it a little bit, but if you've never done calculus before, that's fine too. Okay? All right, so let's look at the first technique. Okay? This is going to be technique A. Find the crossover point. And again, over here on Wolfram Alpha, that means finding this point right here. So how do you find those two? How do you find points where two functions intersect? You set them equal to each other. F of n is equal to g of n, right? And then you find all the values of n that satisfy those two things. Remind me that it's 175n squared plus 50n plus 1. So 175n squared plus 50n plus 1, right, is equal to n cubed. Right? So how would you go about finding this? How would you go about finding all n's that satisfy this equation? Well, what I would do is I would put everything onto one side here first. N cubed minus 175n squared minus 50n plus 1, or minus 1, excuse me. Minus 1 is equal to 0. Now, does it look familiar? How do you find all the n's that satisfy this thing? You need to find what? Need to find roots. Okay? You need to find all the n that satisfy this. Does anybody at the top of their head remember how to find roots for a cubic equation? I don't. So let's change the problem a little bit. Right? Otherwise, I would throw this into a solver. Let me go ahead and get rid of that really annoying minus 1. All right? Without loss of generality, we can do that because we're taking off a 1. We can always add 1 back in later on after we've solved all the roots. And then we're just off by 1 on all of our equations. Right? Who cares? Now, it's really easy to find one root. Tell me one value of n that satisfies this equation. 0. Good. N is equal to 0 is 1 root. 1 root. Visually, is that the root that I'm looking for? Well, both of these intersect down here at 0, but that's not the one I'm looking for. The one I'm looking for is right there. Right? All right. Well, that means that I can factor out that root. And I get n squared minus 175n minus 50 is equal to 0. Find the other two roots for me. Now do you know how to do this off the top of your head? Oh, no? This is a quadratic equation, right? What tool do you have to find roots of a quadratic equation? The quadratic formula. So what is that again? Negative b plus minus square root b squared minus 4ac all over 2a. Is that correct? All right, we're good. So what is b in this case? 175, negative 175, so that'll be 175 plus minus square root of b squared, that's 175 squared, minus 4 times a is 1, times c is going to be 50, so that ends up being 200. All over 2a, which is 2. I don't like that. Pull out your calculators and do it. Wolfram alpha. Roots of, what is it going to be? N squared minus 175n minus 50. There it is. There's the minus root. Is that the one that we're looking for, by the way? Let's go back over here. Over here, I never graphed the negative part of this. What if I did graph the negative part of this? You would see that it intersects somewhere over there as well. Oops, did I screw up? Come on, why are you not doing it? Correct. Over here somewhere, right? Anyway, why didn't I graph anything in the negative side? What is n quantifying again? An input size. Is there such thing as a negatively sized input? Nope. So we're gonna completely ignore that negative root right there, right? Because it's on the wrong side. What about this thing right here? 175.285. Right? So this is going to be n is equal to 175.285. Right? There's the root that I'm looking for. There's the crossover point. Right? What I can now say is that for all n greater than or equal to, careful here, these are all integers. So I need to go up 1. 176, which is my n naught. F of n is less than or equal to c sub g sub n for c being 1. Now, what was my f of n? What was my g of n? My f of n was, what was it again? 175 n squared. 175 n squared minus, or plus 50? Yeah, plus 50n plus 1 is less than or equal to n cubed for c being 1. Right? That's what we've essentially done. I've found my n naught, right? I fixed implicitly, I fixed c to be 1. And I found n naught to be 176. And that's what the definition of big O analysis is. You need to find that point at which one function will always be greater than or equal to the other function, with this constant sitting out front here. I've got two unknowns. I've got c and n naught. You fix one and you find the other, right? There are an infinite number of pairs that this will work for, right? You just have to find two of them. The other technique, the second technique here, is going the opposite direction. We're going to fix n naught to be 1, okay? So this is going to be the second technique. Technique B. We're going to fix n naught to be, say, 0 or 1 or 2 or something small like that. And now what we need to do is we need to find c, some constant c. It doesn't have to be an integer here, but it's going to be a positive constant. So r plus here, right? So that f of n is less than or equal to c sub g sub n for all n greater than or equal to n naught, which is 0. Right? What does that look like visually over here? Right? Let me go back. I don't need that one anymore. Right? There's my crossover point. What I'm going to do is I'm going to change the crossover point by making this function bigger. Right? How can I make it bigger? By multiplying it by a constant. Let's make it 3 times as big. What does that do to the crossover point? It moves it back. Right? Let me take another step here. Let me make it only twice as big. Right? Now remember that it was over here somewhere, and I've moved it back. Let me go ahead and look at both of those for reference. Right? So I'm going to graph all 3 of these things. There's the original. That's the original crossover point. By multiplying it by 2 here, what I've done is I've moved that crossover point down to here. Well, what's to stop me from doing it again? 3 times n cubed. There we go. And I'm going to go ahead and zoom in over 100 here. Right? I'm going to zoom in, zoom in, zoom in. Do you see that the original crossover point is now over here somewhere at 176 or 75, right? And I pushed it back here, and then I pushed it back again. Let's keep doing that. 4 times n cubed. And here I'm going to zoom in even further here onto 50. Right? There. I keep pushing it back. That's almost pushed back all the way to 0. Visually, that's what we're doing here. We're making the function bigger. Algebraically, it's even simpler. Right? Here's how you do it. You set up an inequality. Here's 175 n squared plus 50n plus 1. We need to eventually make that less than or equal to c times n cubed, somehow, right? That's where we want to be. I want to find that c. That's my roadmap. That's where I want to end up, okay? I need to make this function look like this function right here by making it bigger, okay? Well, first of all, let's focus on, I don't know, what about this term right here? How could I make 1 bigger? I could make it into 2. I could make it into 3. I could make it into any number that I want, right? I could make this 175n squared plus 50n plus, 50. That doesn't really get me anywhere because I want to collapse these 3 terms into 1 term that looks something like this. So what could I do with that term at the end there? I could what? I could multiply it by n. I could replace it, I could go all the way to n cubed. Let's go ahead and hold off on that for a second though, right? I can make it n. Why? Here's my justification. Why? Here we go. N is greater than or equal to 0. Let me get rid of all of that. There we go. Why? Because n is greater than or equal to 1 for all n greater than or equal to 1. Right? Now remember I said we're going to end up z being 0, but that's okay. We're just going to make it bigger. Right? We're going to change ours from 0 to 1. That's going to be our crossover point. Right? All right, that simplifies things. 175n squared plus 51n now. I took 3 terms and now I'm down to 2 terms, and it looks more like this in that I don't have this scalar term anymore. Continue. Do another trick here. I can make this less than or equal to 175n squared plus 51n squared. Why? Because n squared is less than or is greater than or equal to n for all n greater than or equal to 0. Right? There's my justification for that one. Right? There's my justification for that one. Right? That's equal to 175, or actually, I've got n squared, right? So 50, it's 226 n squared. There we go. Doesn't quite look like this one yet. There is a constant term here, but this is n squared and this is n cubed. Keep going. Multiply by n. This is less than or equal to 226 n cubed for all n greater than or equal to 1. In fact, it's greater than or equal to 0 too. Right? Now that's equal to 226 n cubed. Actually, I'm already there. I don't need any more. Right? So my conclusion is for c being 226 and n naught being 1, the inequality holds, and f of n, as I originally wrote it, is big O of g of n. All you're doing is making it bigger, 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 right? And all you're doing is finding the c out front, making sure that any n that you have, satisfies that inequality. Technique C requires some calculus. You set up a limit. The limit as n tends towards infinity of these two functions, f of n over g of n, is going to be one of three things. If you've never had calculus, that's okay. This is going to be super, super simple anyway. Okay? So one of three things can happen here. First of all, this one can grow much, much faster than this one down here. What happens when that happens? It diverges off to infinity. You could have something that is an equal growth rate, right? In which case it would converge to some constant greater than 0. You could have the one on the bottom growing much, much faster than the one on top, in which case this converges to 0. Right? Again, if you've never had calculus, that's okay. This is just another technique. Right? If it diverges off to infinity, that means that f of n is growing much, much faster. That means that g sub n is big O of f of n. Right? Why? Because the top is growing much faster, and therefore it's the bigger function. Right? Just the opposite here. If the bottom is growing much faster, that means that this is going down to 0. And therefore, f of n is big O of g of n. Now, what if they have a balance? This one grows at exactly the same rate as this one down here. That means that f of n is big O of g of n, and g of n is big O of f of n. Both of them are true. So over here, this one is true, but this one is not true. If you've got 0, then this one is true and this one is not true. But if they both converge to a constant, then both of them are true. Right? By the way, there are other ways of putting this. This means that f of n is big omega. This one is big theta, but this one is still big O, or O is omicron. Again, that's technique C. We're not expecting that too much, but it can be really, really helpful and easy. Because now take a look at what we just did. 175 n squared plus 50n plus 1 all over n cubed. What is the limit as n tends towards infinity of this expression right here? Those of you that have had calc will see that the limit can be broken up, because the limit of sums is equal to the sum of limits. And this is 175 n squared all over n cubed plus the limit as n tends towards infinity of 50n over n cubed plus the limit as n tends towards infinity of 1 over n cubed. Tell me about this one right here. Is the top growing at all? The bottom is, right? So what is the limit of this one? It converges to 0. What about over here? This one will cancel with this one, and you are left with n squared here. Now is the top, that's just algebra, by the way. Now the top is not growing, but the bottom is growing. You have the same exact scenario here. It's going to be 0. Now what about over here? N squared will cancel with that. And you've got 175 on top, n on the bottom. That's also going to be growing on the bottom, not on the top, and therefore it converges to 0. Right? The limit as n tends towards infinity of f of n over g of n is going to be 0. According to this, what does that say? The same thing that we just proved using the other two techniques. Right? F of n is big O of g of n. All three of these techniques conformed with our intuition that something that is cubic is definitely going to be outgrowing something that is quadratic. Okay? We might end up doing a few more exercises later on, but let's go ahead and again quantify these techniques. Approach A is you are finding a crossover point. You are fixing C to be 1 or something, right? And then finding the n naught, right? The point, the last point, the largest, that is biggest point where the two functions intersect. That's all you're doing. Find roots. Find roots. That can be really, really easy if you have very, very, nice behaved functions. What if I gave you this? What if I gave you something that looked like this? Let's just say something random here. N to the 40th plus 5n to the 30th plus 8n to the 7th plus 4n to the, third plus 8n squared plus 1. Right? Can you find a root? Can you find all the roots there? How many roots are there going to be, by the way? If it's a quadratic equation, how many roots are there? It's degree 2 polynomial, so you found 2 roots. How many roots are you going to find here? 40 of them, right? Do you want to do that? No. So this is going to be involving finding a lot of roots. It's easy to use, easy if only if finding the roots are easy, is easy, right? Can you find roots of, say, n squared plus 3n plus log n? Find the roots of that thing, right? We've got an exponential function here, a logarithmic function here. We've got a poly exponential function here. Do you want to find the values for n for which this intersects at 0? Gross. If you did have something like this, though, what could you do? What did I just do? I used Wolfram Alpha, right? Use a solver to do something like that, okay? So technique B is probably going to be your go-to, right? Here, what you're doing, you are fixing an n naught, right? And possibly changing it, right? And then finding a C, right? In other words, you set up an inequality, and simply make it bigger and bigger until it matches C times G sub n. Matches. There we go. Right? This is much easier. This is the much easier technique. All you have to do is make it bigger. Right? Again, technique C, you set up a limit. Right? Requires some calculus. Now, some limits are obvious. All right, are obvious. If the numerator or denominator are growing, but the other is not, then it is obvious. Right? But what about some things? For example, calc folks, excuse me. Limit as n tends towards infinity of n over, say, log n. Right? All right, what's our intuition here, first of all? N versus log n. Which one of those is the greater growing function? N, okay, I agree with that. So what we're going to do is we're going to switch these out. Let's go ahead and switch them. I'm going to put log on top and n on the bottom, because what I want to show is that log of n, and remember it's base 2 implicitly, is order n. Okay? It doesn't matter. You could have switched these around and taken the limit, and you would have come up with the exact same the conclusion here. Right? But help me out. This is growing on the top. This is growing on the bottom. Are they converging to something? I don't know. How would you deal with this in calculus, calc folks? There is a co-requisite for calculus 1 here. Right? Help me out. What would you do? A monotone increasing function on the top, a monotone increasing function on the bottom. There's this rule that you apply. What was it called? I don't know what nationality he is, but no? The L'Hopital. And there are 2 diacritics here somewhere. I have no idea. Right? L'Hopital's law. What is it? Limit as n tends towards infinity. Right? What do you do to the top? Take the first derivative. What do you do to the bottom? Take the first derivative. What's the first derivative of n? That's easy. 1. What's the first derivative of log of n? Okay. Log, remember, base 2 of n, what's the first derivative there? What if I said ln of n? What's the first derivative of that? Do you know? That one you do memorize in calc, right? What is it? 1 over n. This one is also 1 over n, but there's a constant sitting out front. 1 over natural log of 2. Right? Let's go ahead and just give that a name, c. Okay? Come back over here. I'll take that c out front, and I'll have 1 over n on the top. What does that equal to now? Limit as n tends towards infinity of this c. I'll just take that c out completely over there. 1 over n. Now we've got a monotone increasing function on the bottom. We've got a constant function on the top. So what is your answer now? What's the limit of this thing? 0. That shows this over here, according to this law that I just set up. Right? If it converges to 0, then we can conclude that f of n is order g of n. How would we do that with the first two techniques? I want to show that log base 2 of n is going to be big O of n. Right? And so what I'm going to do is I'm going to assume, I don't know, actually, let's go ahead and look at the plot of these two things. Let's go ahead and go with log base 2 of n, and n is equal to 0 up to 10, let's say. Very small input sizes here. There we go. So immediately, do these ever intersect? No. By the way, is the negative ever defined? Careful here. Is 0 defined? No. So you're going to have to modify your definition to start at 1 immediately. Right? This one is obvious from the get-go. Right? If you want to set up an inequality here, log of n is less than or equal to n for c being 1 and for n naught being, careful here. For all n naught being 0, log of n is less than or equal to n for all, for all n greater than or equal to n naught, which is 0. Is that true? Careful. Is log of n defined for 0? Nope. So we can't use that. What we have to do is we have to increase our n naught to being 1. That's okay. It's okay to find another crossover point, right? Or a point here at which both functions are defined, but one is always going to be greater than. Okay? So sometimes you have to be careful because they might not necessarily intersect here. Okay? But that one is also clear from the definition. Okay? All right, so you may require some, other techniques, right? And I have no idea how to spell it, L'Hopital, right? Maybe that's close enough. I can't do diacritics. L'Hopital's rule, right? Etc. Right? So be careful. How about nah, we won't need to do that example. But here's some categories of functions that we've already covered before. Right? You can have constants, which would be just a formula computation. If you needed to compute, say, the roots of a quadratic equation, that's just a formula, actually 2 formulas. You're plugging and chugging. Right? That's going to be order 1, which is constant. We don't write order, say, 5. Why? Because that's the same thing as writing order 1. It's all constants. It's every function that has a constant or 0 rate of growth, basically. We have logarithmic. One example of that would be binary search. Right? We have linear. One example of that would be linear search. We have quasi-linear, efficient sorting algorithms such as merge sort and quick sort, something that we're going to look at eventually. You have quadratic, the bad sorting algorithms, selection sort, insertion sort, bubble sort, anything basically other than quick sort, merge sort, and tim sort. You have cubic algorithms. I don't know, have you done transitive closure in 235 yet? Like, you have? Okay. There's a transitive closure algorithm, Varshall's algorithm, or maybe Varshall-Floyd or something, right? And that's going to be cubic. Why? Because it operates on a matrix, right? You have things, more generally here, you have polynomial. Any n to the k for some fixed k. You have exponentials, and not all exponentials are the same to within a constant, right? And you have super exponentials, order n factorial, for example, if you're trying every single possible permutation. Right? Obviously, anything here and above is not going to be tractable for most data, right? In other words, we've already seen an example here where quadratic was not acceptable. It would have taken us an estimate of 20 years to operate on a list of only 1 billion elements. Right? Unfortunately, quasi-linear is also slow, but that's as best we can do for sorting algorithms. If you're looking for fast algorithms, you're always looking for linear algorithms, constant algorithms, or if you're lucky enough, constant algorithms, or logarithmic, and then if you're lucky enough, constant algorithms, right? Super exponential is not at all tractable, right? If you even get up to, say, 100, trying to arrange 100 things, or even 52, right? A deck of 52 cards, the Mamaluke deck, right? 52 cards, 52 factorial is more than the number of atoms in the known universe. You would not even be able to build a computer to hold all that information, right? Because it would be larger than the known universe. Right? This is not at all acceptable, right? For maybe 6, 7, 8, maybe even 10, right? Yeah, fine. But even getting up to like 50 or 52, no, you're beyond, right? That would not be tractable in any computer that is even conceivable, okay? All right, we'll get some more practice on this maybe on Wednesday.